Just a little bit of information about the hub and what we've been doing. The hub started in 2008 as a public-private partnership, so we had some government funding at its inception. And it was set up to facilitate the delivery of zero-carbon homes and also to devise the standards along the way. So the hub is not the organisation that sets carbon compliance or fabric efficiency standards, but it is the organisation that's brought together all of the people who are involved in delivering homes. And it's sought very hard to ensure that standards aren't just devised by people in white coats at the BRE who don't have experience of building and delivering homes, in commercial conditions, and with Daniel's very good definition of what the performance gap is, with all of the variability of building on a building site rather than building, in the controlled environment of a factory. And the major kind of publications and pieces of, in a way, standards that have been built into legislation that the hub have devised are firstly the Fabric Energy Efficiency Standard. In 2009, there was a growing realization that there is a tendency to use technology to offset inherently wasteful design, and that actually the first plank of any good low-carbon solution should be one that gets fabric right and deals with demand reduction. We then did a very extensive piece of work here in 2010, looking at the modelling tools, trying to see whether the SAP tool, which started life as a kind of benchmarking tool for comparing energy usage across the country, whether that was a sophisticated enough model for designing and delivering zero-carbon homes. And we tested that against things like PHPP and some of the dynamic modelling that was available. And then building on the kind of carbon hierarchy, in 2011, we looked at what reasonable standard of carbon compliance could be set across the country. So recognizing that not all homes can be autonomous zero-carbon homes. In other words, making an allowance for different topography, different locations, the fact that there might be different urban design or different density conditions that actually constrain carbon compliance. So trying to set a reasonable level that could be applied across the country. And that piece of work actually was one of the most controversial, because people then started to say, well, the definition of a zero-carbon home seems to be very low compared with everybody's expectation and ambition in 2006. And one of the compromises that the industry group arrived at really was a proposal that the standard that we agreed was achievable was actually an as-built standard rather than a theoretical standard. So that, for the first time in England building regulations really, is a diversion from demonstrating compliance with a theoretical model at the beginning of the process to demonstrating compliance at the end of a process with some kind of testing methodology, some kind of accreditation that says what we've built is actually what we intended to build. And the background for this really is a whole series of research projects, all flawed to some extent in that they only have a very small sample to study, but all arriving at the same conclusions. So work by the EST looking at seasonal efficiency of boilers in situ, looking at the efficiencies of heat pumps, work by Leeds Metropolitan University at Stamford Brook, which actually was the kind of foundation for revisions to the 2010 building regulations, recognising things like party wall thermal bypass, and work that I've done for Joseph Rowntree Foundation looking at building prototype homes and testing them and evaluating the different construction methodologies. And this growing body of evidence all points in the same direction, that there is a fairly substantial but not quantified gap between what we predict and what we actually build. Some of the evidence that was gathered for the carbon compliance report in 2010 drew very heavily on a series of tests by Leeds Met, which are really only testing the building fabric, so not testing building services, but just looking at the performance of the home. And Leeds Met have devised a test which really establishes a whole house U-value. Again, what we see is that of the 16 or so tested homes, none of them matches the predicted performance. some of the ones that actually show the greatest deviation are very well-known demonstration projects at, for instance, the BRE Innovation Park. And interestingly, some of the ones that do very well have been built by small builders with a really good control of their supply chain and real familiarity with the construction techniques that they're using. Fortunately for me, my homes are over at this right-hand end, but some of them are alarming in their difference. You know, a 200% difference between what's predicted in SAP and what's actually delivered. And that's just on the heating. That doesn't look at ventilation, hot water usage, any of the other mechanisms for energy usage in the home. Now, at EcoBuild last year, Andrew Stunnell, the then Minister in England for Building Regs, ruffled a few feathers by comparing the house building industry to British Leyland in 1979. You know, the implication being that every house that rolled off the production line was broken or flawed in some kind of way. And unfortunately, what that served to do a little bit was to polarize the discussion a bit too much into a debate about whether house builders can actually build what's designed on the drawings, whether they can actually build what's specified. And it seems to me, and sort of working for the Hub for 5 years now, I'm getting a little tired of all the discussions about the journey that we're on, that we ought to have a slightly better kind of metaphor for what the performance gap actually is. Because there are lots of people involved in the design and delivery of homes that are providing design information, suppliers, manufacturers, SAP assessors, the concept designer starting at not a fictitious tube station, Turnham Green, but not actually involved very much in the construction stages. And actually, although everyone's talking about it's between construction and handover, there is a vast and not well understood gap in knowledge from all of the people contributing to the early stage processes. And actually, we suspect there are some flaws in some of the conventions that we use. So, for instance, this home, which is a well-constructed home, the builder's not at fault here at all. But the designer, I suspect, doesn't understand the implications of some of the design decisions. How many architects, for instance, would know how to calculate a U-value for timber frame and what assumptions are made about the timber fraction within the frame? Most architects probably think timber is a good insulator. Quite wrong in a low-energy home. The conventions allow the studs to be at about 600 centres. In this home, they're all at 450 centres. There's considerably more solid timber in the dwelling. There are point loads that are being dealt with by steel and duplication of timbers. So actually, the quantity of solid timber in this dwelling is about double what the U-value convention allows for. How many SAP assessors would know how to calculate the thermal bridge at those ridge and valley details with a steel supporting the timber roof plate? There are lots of things here in a well-constructed dwelling that are undermining the actual predicted performance in terms of the prediction tool, the SAP tool. And what Lees Met found at Elm Tree Mews, the Joseph Rowntree project, was that about 25% of the external wall was solid timber, whereas the designers had predicted around 10 to 12.5%. Now, you might say, well, this is all just thermal bridging, and is this really a big issue in the overall scheme of things? But what we're finding in detached low-energy homes is that thermal bridging accounts for about 35% of the heat loss. And this is the reason why, when you get to the standard we're at now, 2010, 2030 regulations, it's not possible to have a recipe. Somehow you've got to find a way of calculating and understanding thermal bridges because their contribution is so significant. So to get back to the work that we've been doing, we assembled a huge number of professional people involved in delivering homes in about 10 different work groups looking at different aspects of the delivery process, right from early conceptual thinking through to verification and testing at the end. And that work really unearthed something between sort of 60 and 80 potential, only speculation, potential flaws in the delivery process of new homes. And they're summarized in our interim report, which was published in the summer of last year. The real issue that emerged is one to do with evidence and measurement. If we suspect that there's a problem and we need to correct it, we need to know where the major incidences are. There's no point, in a way, worrying about 65 different issues if only half a dozen of them are really making a major contribution. So the second phase of the project has been one of evidence collection. And it seems to us that actually the evidence at the moment that's available is in very limited sources, and it's distributed in different ways. You know, there are a small number of research projects. There's a lot of industry knowledge, which is mainly anecdotal. There's a lot of specialist supplier information, which is not in the public domain, for good reasons very often. And there's a lot of information that's been collected by individual house builders, but for commercial reasons that isn't being shared. And what has been really encouraging about the project is that in the evidence collection stage, you know, a lot of work is done on reviewing existing literature, but we have also started a process of visiting sites under construction with the cooperation of 3 or 4 of the major house builders and undertaking something like a kind of Ofsted test, where an Ofsted review, where the site team are interviewed, the design information is reviewed, the people who devise that design information are interviewed, the site walk-arounds, recording, looking at what's being built, and then there is an audit of the SAP performance to see whether the SAP assumptions that were made are actually being delivered on site. And the really interesting thing about that is that there are some very common themes coming forward, and that the house builders who have participated in that process have already kind of stepped one step forward into recognizing and solving this issue. So, an example. This is from one of the TSB building performance evaluation projects, and so this will all be written up. In fact, some of it's already available in the public domain, but by the time of EcoBuild, the Zero Carbon Hub will have done a major study and publication on this particular project. But what we saw when we reviewed the information here is very interesting. First of all, homes being built in 2009 to a SAP 2005 standard. Not great, really. But absolutely no difference between the design stage SAP and the as-built SAP. English building regulations have required since 2006 that you submit to builder control a record of what you actually did. So if you change the boiler, if you've got your as-built air pressure test data, you rework the SAP and you record what was actually constructed. On this project, nothing declared, absolutely everything as was designed. And a claim, in terms of thermal bridging, that accredited details had been used. Now, this is a mid-floor apartment, so my point about the percentage of heat loss through thermal bridging doesn't apply so much because there's only one external wall where there are thermal bridging losses. But when we audited the design and applied SAP 2009, we saw an alarming difference between what the designers thought the building would be doing and what it was actually doing. And we also noted that on site, none of the accredited details had been employed. So claimed in SAP, but not delivered on site. We also noted that the actual air pressure test for building regs submission was about twice the value that had been put into the predicted SAP and the as-built one. Then when we did an audit based on measurement, so building in the U values that we tested on site, the air pressure test, the thermal bridging that we knew about, we actually ended up in a result which was about 60% higher than was predicted. And that was verified by some coheat test results that we had. And the kind of things that we saw had gone wrong in a design review, they're not rocket science, they're not that difficult. SAP assessment assumed 300 mil of insulation, but if you look at this section, you can see that at least a third of the house, it's just not possible to achieve 300 mil of insulation. It's a problem in every eaves detail of every low-pitched dwelling. You simply cannot get the insulation to the level that has been assumed. Voids above the corridor here, built in as it went along, no mechanism for installing insulation there. Actually, when we did thermal imaging, we found there was no insulation in this position at all. The claimed use of accredited details. There are no accredited details for this particular construction, which assumed that the air tightness barrier was at the line of a secondary ceiling point. In fact, there were no construction details on this site at all. The only details they had were robust details for Part E. And we've already discovered in 2006 that a good detail for Part E is not necessarily a good thermal detail. we did some thermal imaging, and my kind of reaction to the design intent was that actually on balconies and external constructions, they'd done quite a good job. They had external columns supporting the balconies, so they were trying to avoid a cold bridge at the balcony connection with the external wall. But actually we saw whopping amounts of heat loss in that position. Part of that, I suspect, is through using a blown lead insulation, which is very difficult to get to distribute equally through a wall, and especially in these very narrow sort of horizontal strips of wall between the threshold of a door and a lintel above. But then when you actually look at the detail that was installed, I don't know if you can see that, that's not even a robust detail. It's nothing like an accredited detail. There's a continuous steel lintel bridging the base of the cavity. The window position is right at the front of the external wall, so not in line with the insulation cavity as it should be. And you can see here, I don't know, it's maybe too bright to see that, but there are small gaps of daylight between the plasterboard and the lintel there. And bearing in mind that they're using the plasterboard lining as the air tightness layer, that's a bit of a nightmare detail anyway. But what I suspect has happened is that on site, the carpenter has said, I can simplify this detail for you. I can build joists for your balcony from the outside bearing on that lintel. And I can make that a much cheaper construction, but all the way along there are now voids between the external wall and the internal. So massive heat loss through a simple balcony detail that probably started out from the designer on the right lines. One of the things that we've been doing in the early stages of the project, and this is where it gets very, very difficult to understand really what's going on in house building, is trying to map some of the processes. So trying not to make generalizations about what a volume house builder does and what a small house builder does, or to try and apply the same lessons from volume house building to, say, an RSL that's commissioning a project through a traditional design and build contract. And we went right back to early stages, and of course you find things right at the very beginning of the process. If the planning authority insists on a 10% renewables contribution, but has no way of enforcing that, or no way of actually verifying that that's been made, it's no surprise that the house builders don't actually honour that commitment. In the site walkarounds, all of the sites that have come forward so far where there's been a renewables commitment, that has been misunderstood. Either energy and carbon have been misunderstood, or much worse, the house builders just said, nobody's going to come back to check. So the PV or the solar thermal doesn't happen. We've been through all of the process, and in a way, I think this is a fairly futile exercise. Both Latham and Egan in the past have tried to rationalize house building and construction processes and make analogies and models with the automotive industry. But actually, the construction industry is not susceptible to this kind of process analysis. What we have concluded is that what we need to emphasize much more are the testing and verification procedures that are available to us. This is the kind of statement that's coming out in things like, government reports, but in a way it's a bit of a generalization. I don't think it's the role of our project to invent processes for house builders. House builders are very good at implementing processes for things like land acquisition and sales. They don't need a group of kind of academics, architects, policymakers telling them how to do things. What we really need to be doing is kind of holding a mirror up to the industry and letting the industry respond to what we've been discovering. The difficulty partly is that we have limited tools. Thermal imaging, despite what the proponents say, is actually a very variable technique, and you have to be extremely experienced in interpreting thermal images to understand what they're saying. The hotspots on a thermal image can be caused by heat transfer through components of construction, but they can also be caused by elements of construction that reflect heat. So you need to know when the thermal image was done that there was a very good difference between internal and external temperature and a good transfer of heat through the construction. Heat flux testing is interesting but quite laborious. Again, you need to have the temperature within the dwelling set very high and constant in relation to an external temperature. And if you really want to know what an in situ U value is, you can't do it with a couple of heat flux sensors, because if you plonk one of them on a stud or a metal stud or a dab of plaster or the point where there's a wall tie, you're going to get a false reading. You really need to have quite a large array of a dozen or maybe 20 heat flux sensors and collect data from them for a long time. So we're still in the realms of research tests rather than industry tests. And the same would be said of the coheat test, which is a very intensive test that takes 4 weeks or so to do during a winter period. It's not something that we can roll out at the end of a sample of, say, 1 in 10 houses to verify its performance. So one of the main objectives of the remainder of the work that this project has to do, and we're reporting on what the industry needs to do in a few months' time, is to actually work on some more robust inline tests that can be adopted by industry very easily with some actual measurable gains in terms of their processes. So one of the things that we advocate on our projects is to do a mid-construction air pressure test. At the moment, the house builder waits until everything's finished, does his air pressure test, fails it, goes back in with loads of mastic, loads of tape, fills a skip with discarded mastic cartridges, all at his cost. It takes ages to explain to a builder that if you did that when your house was watertight, on your external envelope was finished, you could make sure that windows, roof, first primary linings, the air tightness there, were all installed in place. You know that if it's breached after that, it's first fixed mechanical. It's the electrical guy. It's the guy installing the services or the renewables. It takes a very long time for the kind of house building industry to recognize that in this project, we could be devising huge ways of introducing efficiencies and making economies on site. This is a slide that I've been given to talk about quite a lot, and I don't really like the kind of cheesy, I didn't draw it like this, and some guy on site has made this kind of incredible artistic kind of, interpretation of how you install ductwork from an MVHR unit to the rest of the home. But then I realised when I tried to take this off, there's actually blocking off the logo of the ventilation unit manufacturer. And it's there for good reason, because he's not culpable. The guy who produced this unit and supplied it to site supplied it with a full set of drawings, which were completely ignored. And in our work, we've been criticised by the house builders, saying, well, you're going around all these sites, so you're just going to assemble a kind of rogues gallery of everything that goes wrong in construction. And I absolutely disagree with that. I think the reason why the NHBC have reacted very quickly to issues to do with ventilation installation is that there are health and safety issues, there are energy running cost issues, there are things that will immediately cause claims on NHBC warranted projects. And it's the fact that these kind of images are circulating that the new guidance has been devised very quickly, a very, very rapid response from NHBC to a potential problem. So, sorry, a very fast canter through various aspects of what we're doing, but that's the end of my talk.